Okay, so we do a lot of examples in our class with the NPN transistor. And when it comes to the PNP, the other kind of transistor, students often have difficulty with it because we don't do a lot of examples. But let me just explain how the process is the same. So here's an NPN circuit. The current flows down through this resistor into the base, and that creates base current, and then the collector current is just beta times that. And what we would do is we'd figure out the voltage across this resistor, which would be 19.3 volts, and then we'd figure out how much the base current is. For the PNP, the analysis is the same. All you have to do is you have to think about that the whole circuit has been flipped over. So the transistor ends up being up at the top, and then the two resistors are connected to ground instead of connected to high voltage. And then the base drive circuit, what you do with the base drive circuit is you figure out the loop from the supply voltage back to the supply voltage. So let me show you how that's redrawn here. So this is how it's drawn with a PNP circuit. So first of all, comparing the two circuits, you can see with the NPN, the one you're familiar with, it's 20 volts down to ground. That injects current into the base, resulting in collector current. With the PNP, we pull current out of the base by providing a path to ground, which causes a larger current to go down the collector. With the NPN, when we redraw the base drive circuit, we do it like this. We draw a loop around the ground. When you do the PNP transistor, you draw a loop around the supply side. And what you can do is how does this make sense? Well, see, this point here is ground. This is 0 volts. The base resistor is connected between 19.3 volts and ground. Well, if I draw that here, I can connect that to ground. Or if I put the supply here at 20 volts, and then this point here would be 0 volts. So I've basically redrawn it with a separate voltage supply, and this is the loop I'm going to solve. So if I look at this loop, if I start right here on the loop, and I go this way around the loop, it would be minus 20 plus 0.7 plus IBRB equals 0. Minus 20 plus 0.7 plus IBRB equals 0. I rearrange this equation to get IB on one side, and what I'm left with is 20 minus 0.7 over RB, which is 19.3 over RB. The collector current is found the same way, as is the emitter current. The only thing to remember is that the emitter is up here. The emitter is still the arrow, and it's connected to the high side of the supply. And then the collector is here, and it's connected to the load or the collector resistor, which goes down to ground. When you do the AC equivalent circuit, which I've shown down here, it's exactly the same. You short the supply, so I would take this point and I would short it to ground, which would take the emitter and it would take it to ground, and you can see over here I've got the emitter. So I put in a box for my transistor. I write down the terminal names, base, collector, emitter. The emitter is over here, so the emitter is grounded. The collector goes out to RC, which then goes to ground, and the base goes to a base resistor, which then goes to ground. So from the AC equivalent circuit, and from there on, solving for Z in, Z out, AV, it's exactly the same. There is no change. The only change is really looking at the loop around the base current as connected to the supply this way instead of being connected to ground. Okay, so what about this one? Well, and again, what you want to do is you want to take an NPN to figure out the voltage divider bias. What we would do is we take an NPN, just clear some of this noise here. So you take an NPN transistor, and then the NPN current flows, most of it goes down here, most of it goes that way. If you want to redraw this circuit in a PNP configuration, what you would do basically is you just take this on the base and you just flip it right over. So the 100K is going to go to the bottom and the 33K is going to go to the top. All the positions of the resistors are going to flip over when I do this. And you can kind of see them here. The 33K is at the top now. Here's the 100K. 500 ohms, 1.5 k ohms. That's how you would draw the NPN transistor, the PNP transistor in the same voltage divider bias configuration. Except now current is going down. Current is now going this way. You pull current out of the base. Most of the current flows in this direction, but a little bit comes through the base, which biases the transistor. For the voltage divider bias, you find RTH and VTH just like you did. The RTH is the same, but for the VTH, what we want to do is we want to solve for the voltage going this way. We want to solve the voltage across this 33K ohm resistor. So we would multiply 20 times 33K over 133, which is 4.96. But I would draw that as going back to the supply. And then I would write my loop equations down here. Minus 4.9 plus 0.7 over the Thevenin resistance. That's here, 34 microamps. I've solved for the base current. The rest of it I see is solved the same, multiply by beta. IE is done the same, multiply by beta plus 1. Transfer your parts over to the AC equivalent circuit one by one. 33K is between base and ground. Here it's between the base and ground. So the AC equivalent circuit ends up being exact. Only real difference is that you do the loop with the voltage across this resistor and you do it around this way. That's how you deal with the PNPs.